In section 5.2, we're going to work on graphing simple rational functions. Simple rational functions are defined as rational functions that have numerators and denominators that never get larger than the first degree equation. So we'll talk about that more in a little bit. But the idea of a rational function in general is a rational function is a function. So it's a function that has one function in the numerator of a fraction and another function in the denominator of a fraction. So what you've got with rational functions is you're inherently talking about fractions pretty much all the time. So we're looking at a function that has a function in the numerator and a function in the denominator of a fraction. Again, when we talk about domain would be the collection of all the inputs or the x values. And the range would be all the outputs or the y values. Again, x is an independent variable and y would be the dependent variable. And then this idea of asymptotes we worked with last semester. The idea of an asymptote is it's a boundary line that my graph will approach, but in most cases never hit. Okay, so I say in most cases because when we move on to general rational functions, there are times when the asymptotes can be crossed. In simple rational functions, they cannot be crossed. Okay, so a type of problem that you might work with that takes the form of a simple rational function would be this problem, where we've got this idea of a 3D printer. So a 3D printer prints, but it prints in 3 dimensions, so it makes models. And a company's going to work on making small displays of engine parts, as you can see in this picture, and they're trying to work out cost per model as a function of the number of models printed. So we're going to take this information when we get to the end of the chapter, and we're going to go ahead and create a model that's in this form, a function that has one function in the numerator and a different function in the denominator. So what will they be? Well, we want to know cost per model. So the function in the numerator would be the cost, and the function in the denominator would be the number of models. All right, so again, reading critically is really important in terms of understanding what it is you're going to do. Cost per model. When you talk about fractions, this is numerator and then the dividing line and then denominator, cost per model. Okay, so some information about simple rational functions. The parent function, again, has a lot less parts than a full function, but it always creates this sort of a graph. It's called a hyperbola. It has 2 branches, and it has 2 asymptotes. It has a vertical asymptote and a horizontal asymptote. And the 2 branches are diagonally symmetrical to each other. So they're symmetrical around this point, which is the intersection of the 2 asymptotes. So when we're in the parent function, then, and the parent function could be, y is equal to a divided by x, which you'll notice is inverse variation. When we're in the parent function, the x-axis is the horizontal asymptote, and the y-axis is the vertical asymptote. And so we are inversely symmetrical around the origin. And what that means is if I measure a distance to the right, say right 1 and up 1, I can find a point, or say right 2 and up a half. I can do the reverse going the other direction. I could go left 1 and down 1, left 2 and down a half, and I'll be in the same point. Or right 1/2 and up 2, I could go left a half and down 2 to create points on my branches. So similar to what we did with quadratic functions where they were symmetrical around the y-axis, now they're inversely symmetrical around the origin. So whatever I do on the right side, I do the opposite thing on the left side of the vertical asymptote. Okay, if I wanted to go ahead and graph in the parent function form, I know that my asymptotes are going to be at the x and y axis. So I'm going to go ahead and I'm going to drop one there and one there. Those are my asymptotes. I know that I'm going to do an input-output table for the right or left side. It doesn't make any difference. I'm going to do the right side, so I'm going to do 1, 2, and 3. It's important to note that the asymptote, the vertical asymptote, defines a value of x that I can't use. See, I can't plug 0 into this function because I can't put 0 in the denominator of a fraction. That's what creates this asymptote. This is a blank spot in my graph because it's a value of x I can't use. Okay, so 3 divided by 1 is 3, 3 divided by 2 is 3 halves, and 3 divided by 3 is 1. So I'm going to go 1, 1, 2, 3, there's a point, 2, 1.5, 3, 1. And my graph is, my branch is going to come in along one asymptote, go through my 3 points, and go out along the other asymptote. That's what it would look like. Now remember I said it was inversely symmetrical around this point, so I went right 1 and up 3. That means I can go left 1 and down 3, 1, 2, 3. I can go right 2 and up 1.5, left 2 and down 1.5, right 3 and up 1, so I go left 3 and down 1, and these are my 3 points. Again, it comes in along the asymptote, passes through the 3 points, and goes out along the other asymptote. If the whole symmetry thing doesn't work for you, you could just pick 3 points on the left side of the axis, so -1, -2, -3, and you're going to get the exact same points that I just got. 3 divided by -1 is -3, that's this point, -1, -3. 3 divided by -2 is -3 halves, and that's this point. And 3 divided by -3 is -1, and that makes this point. So it doesn't matter whether you use 2 input-output tables or whether you use symmetry. Symmetry is just a chance for you to sort of do it all a little bit faster. It's sort of a shortcut. Okay, so go ahead and practice graphing in the parent form. It's a very simple form. Do problems 5 and 6, and then come on back and we'll work with the fully fleshed out form of simple rational functions. Okay, so they're outside of the parent form, in the full form, there are 2 different types of simple rational function forms. This is one, y is equal to a divided by x minus h plus k, and you see that we've got these values of h and k back. Again, h and k represent a shift. H is a horizontal shift and k is a vertical shift. Okay, and what this shift moves is it moves that point that we are symmetrical around. So this point here will move h to the right and up k. Okay, h and k. The equations for these asymptotes will be x equals h and y equals k, but what that creates is a movement like we had before with square root functions, cube root functions, exponential functions, where h and k represented shifts to the right or left and up or down. Okay, and what it's shifting is the intersection point of the 2 asymptotes. Okay, so the steps to go ahead and graph this is identify h and k and draw in the asymptotes, x equals h and y equals k. Then go ahead and plot points on the left. I would use an input-output table to the left or right, and then match to the other side using symmetry, and then draw your 2 branches. So as I go ahead and do that, I want to identify h and k. So in this case, h is equal to 4, and k is equal to -1. Remembering that if I see -4, right, then it's going to be the opposite of that for h, and k is going to be exactly what I see. Okay, then I would go ahead and draw in those asymptotes. H is equal to 4, so that would be x is equal to 1, 2, 3, 4. x is equal to h, there's one asymptote. Y is equal to k, so y is equal to -1. So these are my asymptotes. So I have x equals 4, and I have y is equal to -1. Now I want to do points to the right or left of my vertical asymptote. Remember, we're symmetrical around this point, the intersection point of the two asymptotes. Okay, so I want to pick points to the right or left. Well, I could pick either, I can pick 5, 6, 7, or I can pick 3, 2, 1. I'm going to pick 3, 2, 1. I just think it'll be a little easier. No magic to it. You should do whichever you think is easier. So when I plug 3 in here, I'll have -3 over 3 minus 4 minus 1. So 3 minus 4 is -1. -3 divided by -1 is 3. And 3 minus 1 is 2. So at this point I'd be at 1, 2. When I put 2 into the same deal, 2 minus 4, I'll have 2 minus 4 is -2. -3 divided by -2 is 3 halves. 3 halves minus 1 is 1 half. So here I'll be at 1 half. And when I put 1 into this, 1 minus 4 is -3. -3 divided by -3 is 1. 1 minus 1 is 0. 0. So these are my 3 points. I'm coming along one asymptote. I go through the 3 points. I go out along the other asymptote. And then I want to compare to this point here. So this point was left 1 and up 1, 2, 3. So I'm going to go right 1 and down 1, 2, 3. That's a point. I went left 2 and up 1.5. So I go right 2 and down 1.5. And I went left 3 and up 1. So I go right 3 and down 1. Again, you could go ahead and do a second input-output table. It doesn't make any difference. You're going to get the same points. Okay, so that's graphing a simple rational function in this form. Okay, so identify h and k, plot the asymptotes based on h and k. The asymptotes are at x is equal to h and y is equal to k. Then pick 3 points to the right or left of the vertical asymptote. Do an input-output table. Plot those points, match to the other side of the vertical asymptote by using inverse symmetry, so do the opposite on the right side that you did on the left side. Create 3 new points. If you don't want to do that, do another input-output table. That's fine. Draw your 2 branches. That's all that's necessary to graph these. So practice in this form. Do problems 16, 17, and 19. Come back and we're going to look at a different form. Okay, in this form we don't have h and k, right? We have, you can see I'm in this form, ax plus b over cx plus d. They're linear functions. Okay, x has never been squared or higher, right? X is never is higher to the first power. So I either have constants or x to the first power. That's what makes them simple rational functions. I know that my vertical asymptote can be found by taking the denominator, cx plus d, and setting it to be equal to 0. Remember, the vertical asymptote happens when I've got a value of x that I can't use. That's the value of x that makes the denominator equal 0. And my horizontal asymptote can be found by taking y is equal to the ratio of the leading coefficients in the numerator and the denominator, so a and c. Okay, so over here I'll set x minus 3 to be equal to 0, so x will be equal to 3. That's my vertical asymptote. 1, 2, 3. X is equal to 3. There's a vertical asymptote. My horizontal asymptote will be the ratio of the leading coefficients, and this is 1x and 1x. So 1 divided by 1, which would be 1. So y is equal to 1 is my horizontal asymptote. Now I want to go ahead and do 3 points to the left or 3 points to the right. I'm going to do the left again because, again, I can do 4, 5, 6, or I can do 2, 1, 0. I'm going to do 2, 1, 0. My value of x has to go in both places, in place of x. So when I do that, I'm going to have 2 plus 4 over 2 minus 3. So I'll have 6 over negative 1, so I'll get negative 6. 1 plus 4 is 5. 1 minus 3 is negative 2, so I have negative 5 halves. So let's go ahead and put these points in. Negative 6. 1, 2, 3, 4, 5, 6. At 1, I'd be at negative 5 halves, so that's 2.5. 1, 2.5. And 0 would be 4 divided by negative 3, so negative 4 thirds, which is 1 1/3. Okay, checking against symmetry from here, I went left 1 and down 7, so I'm going to go right 1 and up 1, 2, 3, 4, 5, 6, 7. I went left 2 and down 1, 2, 3.5. So I'll go right 2 and up 1, 2, 3.5. I went left 3 and down 1, 2 and a third. So I'm going to go right 3 and up 1, 2 and a third. Draw my branches through the points, in along the asymptote, through the points, out along the other asymptote. And that's how you graph these functions. So you have to set the denominator to be equal to 0 to find the vertical asymptote. The horizontal asymptote is the ratio of the leading coefficient in the numerator to the leading coefficient in the denominator. But again, we put in the asymptotes, then we do an input-output table, match the other side with symmetry. So the thing that changed is how we found the asymptotes. The thing that was the same is how we find the points. Okay, so go ahead and practice this form. Do problems 32 and 33 and then come back. And let's go ahead and solve this problem that we discussed at the beginning of the chapter. So the first thing I want to do, remember, for me to do cost per model, I have to find the cost, an equation for the cost, an equation for the number of models. So when I do cost, I have to pay $24,000 for the printer, and each model costs me $300. So what's going to change here, my variable is going to be how many models, right? The number of models. So if we set the number of models to be equal to X, let's say, then I know that the cost will be the cost per model, 300, times the number of models, that's X, plus the cost of the printer, 24,000. That's the cost that I spend on the models. And then the denominator is simple. You see the denominator was number of models, but that's also my variable. So it's just going to be over X. So here's my model. Okay, so now the next step in this problem is they want me to graph the function. So I'm going to go ahead and I'm going to copy this. So here's my function, and I would want to see now which of the models does this match. So let's go back and take a look at those models really quick. So you see this has a linear equation over a linear equation. That makes sense. And this other model has, okay, the big difference is, see, this has a constant in the numerator. You notice there's no value of X here. No variable in the numerator. Instead, you have a constant. This one has a variable in the numerator. This one doesn't have a variable in the numerator. So let's look at my equation. Okay, I have the variable in the numerator and the variable in the denominator. Okay, so I'm in the second form. That helps me figure it out. So I know that my vertical asymptote can be found by setting the denominator to be equal to 0, x equals 0. Well, that's great. That's a very easy to do. I don't have a lot of extra work to do. So x is equal to 0 creates my asymptote. And then my horizontal asymptote will be y is equal to the leading coefficient in the numerator divided by the leading coefficient in the denominator. That's 300. So let's say that we're going to use x in hundreds. Okay, so I can go ahead and go y is equal to, or x and y in 300 in hundreds. So 1, 2, 3. Oops, I'm sorry, I wanted a line there. Okay, so now I have my asymptotes in. So if we go ahead and start working with creating an input-output table in order to graph this. Now, what's unique about this is when you think about these values of x, I'm going to do number of models 1, 2, 3, 4, 5, and then this is going to be in y is hundreds of dollars times 100. Okay, that's the way I've set this up. And then when you think about it, when you think about the left branch of this, is the left branch really going to matter? It's really not, because I can't make negative numbers of models. Remember, this is 1 model, 2 model, 3 model, 4. I can't make -1 models. I can't do that. Okay, so when you think about this, I can relatively ignore the left half of this graph and focus simply on what's happening over here. So if we start looking at making 1, 2, or 3 models, when I make one model, I'm going to have 300 plus 24,000 divided by 1. So that's going to be 24,300. When I make 2, I'll have 600 plus 24,000. So that's 24,600 divided by 2. That's 12,300. And when I make 3, I'll have 900. So 24,900 divided by 3. So that's 8,300. And you can see pretty quick that these points are up here pretty high on my graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 1,000 right here. So most of my graph is way up here. Okay, so let's say the 24,000 is there. Here we're probably about here for my 12,300. But over here 3, we're at 1, 2, 3, 4, 5, 6, 7, 8, and a third like that. So here's the way my graph is going to come in. Right? And it's going to go out along that asymptote. So when you think about this, what happens to the average cost as we make more models? You can see that the more models I make, the lower the average cost becomes. So it's going to become lower. Okay, and that's sort of working through one of these models. Remember, we took the supplied information. I'm working with 2 separate ideas here that make a fraction. You'll notice I didn't try to write the whole fraction. I worked on the numerator first, then I made the denominator, so it's easier if you take bigger tasks and you chunk them up into smaller tasks. Then we took the equation, identified which type of simple rational function it was, so I could identify the asymptotes correctly, plotted the asymptotes in, created my input-output table. You notice I thought about it. I went, well, I can't make negative models, so I didn't bother doing the left side of the graph. You could have done it, but it might have been confusing to you, and it would have been a lot of extra work that was unnecessary. Okay, so try to keep a practical sense in thinking about the problems as you're working, and it'll help you do work that you don't, not do work that you don't need to do.